Are we alone in the universe? The universe is vast, and the possibility of intelligent life existing beyond our own planet has captured the imagination of humanity for centuries. But if there are so many stars and planets out there, why haven't we found any signs of extraterrestrial life yet? This is the essence of the Fermi paradox, a mystery that has puzzled scientists and philosophers for decades. Despite numerous efforts to search for signs of other civilizations, we have yet to find convincing evidence of their existence. So where are they? The Fermi paradox raises important questions about the nature of intelligence, the fate of civilizations, and the potential for communication and contact with other worlds. In this exploration of the paradox, we will dive into the possibilities, the mysteries, and the captivating unknowns that continue to captivate and intrigue us all. The Fermi paradox is a complex and multifaceted problem that can be summarized as the apparent contradiction between the high probability of the existence of extraterrestrial civilizations and the lack of evidence and contact with them. To understand the paradox, it is important to first consider the vastness of the universe. The observable universe is estimated to contain at least 100 billion galaxies, each containing billions of stars. Many of these stars are likely to have planets orbiting them, and some of these planets may be in the habitable zone where conditions are suitable for life as we know it. Given these vast numbers, the probability of there being other habitable planets in the universe is high. In fact, some estimates suggest that there could be as many as 10 billion habitable planets in the Milky Way galaxy alone. Furthermore, the universe has been around for approximately 13 billion years, providing plenty of time for the evolution of intelligent life. However, despite these favorable conditions, we have yet to find any convincing evidence of the existence of extraterrestrial civilizations. This is where the Fermi paradox comes in. If there are so many habitable planets and so much time for the evolution of intelligent life, why have we not seen any evidence of it? Why haven't we received any radio signals or other signs of intelligent life? The paradox was first articulated by physicist Enrico Fermi in 1950 during a conversation with colleagues at the Los Alamos National Laboratory. Fermi asked, "Where is everybody?" He was referring to the fact that, despite the high probability of the existence of extraterrestrial civilizations, we have found no evidence of their presence. So why haven't we found evidence of extraterrestrial life? There are several possible explanations. The first is the rare earth hypothesis. This hypothesis suggests that complex life, like humans, is rare in the universe due to a combination of factors such as the need for a stable planetary environment, the right type of star, and a favorable position in the galaxy. The rare earth hypothesis is a scientific theory that proposes that the emergence of complex, intelligent life on Earth was an extremely rare and unlikely event, and that similar life forms may be exceedingly rare or even non-existent throughout the universe. This theory takes into account a variety of factors that were necessary for life to emerge and evolve on Earth, and suggests that these factors may be extremely unlikely to occur in other planetary systems. One of the key factors considered by the rare earth hypothesis is the location of Earth within our own solar system. Earth is located in the habitable zone, which is the range of distances from a star where a planet can maintain liquid water on its surface, a crucial requirement for the emergence and evolution of life as we know it. The habitable zone is dependent on a number of factors, including the mass and temperature of the star, the size and composition of the planet, and the composition of the planet's atmosphere. According to the rare earth hypothesis, the combination of factors that allowed Earth to be located in the habitable zone is extremely rare and may not exist in many other star systems. The rare earth hypothesis also considers the role of the Moon in the emergence and evolution of life on Earth. The Moon has played a critical role in stabilizing the Earth's axial tilt, which has prevented extreme variations in the planet's climate and allowed life to flourish. The rare Earth hypothesis suggests that the presence of a large moon like ours may be a rare occurrence in the universe, and that many other planets may not have this stabilizing factor. Another important factor considered by the rare Earth hypothesis is the role of plate tectonics in the emergence and evolution of life on Earth. Plate tectonics is the process by which the Earth's crust is broken into plates that move and interact with each other. This process is important for the cycling of nutrients and the regulation of the Earth's climate, both of which are necessary for the emergence and evolution of life. The rare Earth hypothesis suggests that plate tectonics may be a rare occurrence in the universe and that many other planets may not have this critical process. Furthermore, the rare Earth hypothesis also emphasizes the importance of the Earth's magnetic field, which acts as a shield against the solar wind, a stream of charged particles that are constantly emitted by the sun. This magnetic field protects the planet from harmful radiation and prevents the atmosphere from being stripped away by the solar wind. Finally, the rare Earth hypothesis takes into account the role of catastrophes in shaping the evolution of life on Earth. The history of life on our planet has been marked by numerous mass extinctions caused by catastrophic events like asteroid impacts and volcanic eruptions. However, these events have also opened up ecological opportunities that have allowed new species to emerge and thrive. The rare Earth hypothesis suggests that while these catastrophes may be common in the universe, the combination of factors that allowed life to emerge and survive them on Earth may be extremely rare. Another explanation is the Great Filter hypothesis. This theory attempts to explain the Fermi paradox by suggesting that there is a filter that prevents intelligent civilizations from developing and/or surviving. The filter is thought to be a series of challenges that must be overcome for a civilization to reach a certain level of development, beyond which it is capable of colonizing other planets and potentially communicating with other intelligent species. According to the Great Filter hypothesis, there are two possible scenarios. Either the filter is behind us, meaning that we have already successfully navigated the challenges and reached the level of development necessary for interstellar communication, or the filter is ahead of us, meaning that we have not yet encountered the challenges and are at risk of being wiped out before we can progress any further. This hypothesis raises important questions about the nature of the universe and our place within it. Moving on, another explanation is the zoo hypothesis. This hypothesis is a possible resolution to the Fermi paradox, which suggests that advanced extraterrestrial civilizations are aware of our existence, but have chosen not to make contact with us for various reasons. This hypothesis suggests that these civilizations are observing us like animals in a zoo, and have deliberately chosen not to interfere with our development or reveal their existence to us. The hypothesis assumes that extraterrestrial civilizations have the capability to detect and observe Earth and our civilization. Instead of making direct contact, they prefer to observe us from a distance, much like a zookeeper observes animals in a zoo. They may also be monitoring us to ensure that we do not pose a threat to the rest of the universe. Another possibility is that advanced civilizations may simply prefer to observe and study developing civilizations like ours, in order to gain insights into the evolution of intelligent life and the development of complex societies. This would be similar to how we study animals in the wild to gain insights into their behavior and biology. Critics of the zoo hypothesis argue that it requires a high degree of coordination and cooperation between multiple advanced civilizations, which may be unlikely given the vast distances and complexities involved. They also point out that it assumes that all advanced civilizations share the same ethical concerns and motivations, which may not be the case. Lastly, the final explanation is the simulation hypothesis. This hypothesis is a philosophical and scientific theory that suggests that our universe and all of its contents, including ourselves, may be part of a simulated reality created by a highly advanced civilization. The basic premise of the simulation hypothesis is that if a civilization becomes advanced enough to create highly sophisticated simulations, they would likely create many such simulations, some of which might include simulated beings with their own consciousness and experiences. These simulated beings might believe that they are living in a physical reality, but in fact, their reality is a simulated construct created by a higher intelligence. Proponents of the simulation hypothesis argue that there are several reasons why such a simulated reality might be created. It could be a form of entertainment for the creators or a way to test theories and ideas in a controlled environment. It could also be a way for a civilization to preserve its knowledge and culture for future generations by creating a simulated archive of their society. Supporters of the simulation hypothesis point to several aspects of our universe that could be interpreted as evidence of a simulated reality. For example, the laws of physics and the fundamental constants of the universe appear to be finely tuned to allow for the existence of life, which some argue could be the result of a simulated environment optimized for the evolution of intelligent beings. Additionally, there are also some philosophical arguments in favor of the simulation hypothesis. For example, it raises questions about the nature of reality and the possibility that we may never be able to truly know whether we are living in a simulation or not. It also challenges our assumptions about free will, since the actions of the inhabitants within the simulation would be determined by the programming of the simulation. Critics of the simulation hypothesis argue that it is highly speculative and lacks any concrete evidence. They also argue that even if our reality were a simulation, it would be impossible for us to detect or prove this fact, as any evidence we observe would be part of the simulated reality. These are just a few of the many proposed solutions to the Fermi paradox. It's important to note that there is still much we still need to learn about the universe, and our understanding of the conditions necessary for the emergence of intelligent life is still evolving. As such, the Fermi paradox remains an important and ongoing subject of study and debate. In conclusion, the Fermi paradox is a fascinating and thought-provoking problem that has challenged our understanding of the universe for decades. It asks fundamental questions about the nature of life, intelligence, and the universe itself. While we have yet to find a definitive answer to the paradox, the search for extraterrestrial life and the exploration of our universe continues to capture the imagination of scientists and the public alike. As we continue to study and explore the cosmos, we may one day find the answers to the Fermi paradox, and in doing so, uncover new insights into the nature of our place in the universe. Until then, the Fermi paradox serves as a reminder of the vastness and mystery of the cosmos, and of the limitless possibilities that await us as we continue to explore and discover the wonders of our universe.